Hello, everybody. Welcome back to G4 Labs Physics, and today we're going to go over force and Newton's first two laws. So, what is force? At a very basic level, a force can be considered a push or a pull applied to an object that causes a change in an acceleration in one direction or a change of direction. It can also cause changes in the shape of an object, and the unit used for force is newtons, or kilograms meters per second squared, and you'll see why later. So immediately we're going to go into Newton's first law. Newton's first law states that an object at rest will stay at rest until acted upon by a force, and the same applies for an object in motion. In other words, if there's no net force acting on the object, it's going to remain in equilibrium. And the term describing an object's tendency to resist a change in motion is known as inertia, which is a qualitative property, and for now all you need to know is that inertia increases with mass. So Newton's second law says that the net force is going to be equal to the mass of the object times the acceleration of the object. And this is a very significant find since we can use this to determine the weight of an object in newtons. Weight will be equal to the mass of the object times gravity. And we can also use it to calculate many other things. And as for the explanation as to why the unit for force is kilograms meters per second squared, well, if you look at the equation F is equal to ma, we get the kilograms from m, and then we have to multiply that by meters per second squared, hence kilogram meters per second squared. Okay, so how do we model force? We model force through free body diagrams, and these diagrams work by labeling all the forces acting on an object. The net or resultant force can be modeled by taking a vector sum of all the components. If this wasn't already gone over in class, you basically use trigonometry to separate the horizontal and vertical components, and then you find the magnitude of the vector using the Pythagorean theorem and the sum of the horizontal and vertical components. And then furthermore, it's also important to note that zero net force or no net force means that the object is in equilibrium. So for our first problem, Jacob is pushing a box with 80 newtons of force and the box weighs 10 kilograms. So then how long will it take for the box to reach a velocity of 64 meters per second? So here's what the free body diagram is going to look like. Do note that gravity and normal force are acting here, which normal force is something we're going to talk about later, but they cancel out. So, and then the net force is going to be in the horizontal. It's going to be F, which is the force that Jacob is applying, right? So yeah, the force body diagram, free body diagram for this one is fairly simple, but it's still good to have it to draw it anyways, since it can be useful for more complex problems. Okay, so to solve the question, we can apply Newton's second law, which is F is equal to ma. And so first we need to rearrange the equation to determine what the acceleration of the box is, right? So F is equal to ma, let's plug in our values. We have 80 is equal to 10 times acceleration. So then acceleration is 80 divided by 10, so then it's going to be 8 meters per second squared, right? And then to get to 64 meters per second divided by, from rest, we do 64 divided by 8, and that gets us 8 seconds, which is our answer. So for different kinds of force, some force can be transmitted through direct contact between two objects. These include tension, normal force, friction, drag, and more, and these are the forces we're mainly going to focus on for this first unit. There are also field forces, which are between two objects even when they aren't in contact, and the well-known example of this is gravity. But there's also the electrostatic force, and there's also magnetism, which I'm sure you guys have seen before. And these forces are modeled and described using fields, which we will get to a few units from now. So tension. Tension is the force an inelastic object experiences when it is being pulled from both sides. For a hanging object, the tension of the string will be equivalent to the force applied by gravity. A 2-kilogram ball is tied to a rope, which has its other end tied to the ceiling. What is the tension in the string that is holding the ball? So if you remember what we mentioned before, for hanging objects, the tension in the string is equivalent to the force that gravity applies. And so to illustrate this, let's look at the force body diagram for the ball, where T is the tension in the rope and it's going upwards, and the W is the weight of the ball and it's going downwards. In order for the ball to remain suspended in the air, there must be no net force on it, right? If there's a net force on it, it would go in the direction the net force is pointing in, and we don't want that, right? And so in order for this to be possible, the string has to pull back with the same force that gravity applies, and that causes the tension in the string to be equal to the weight of the object, magnitude-wise. So then we can do our calculation. So the force of tension is going to be gravity, because that's where our magnitude of our acceleration is coming from, and then times 2, which is the weight of the object, and that will, if you do the math, that'll get you 19.6 newtons. Okay, so here's a slightly trickier problem. A bird is sitting on the midpoint of a rope that is tied to two ends. Assuming the weight of the bird is W and the tension in the rope is T, what is the expression for the tension in the rope? Okay, so this one, it is crucial to draw the free body diagram. So we can see that in order to counteract the weight of the bird, because the bird's in equilibrium, the rope has to pull both ways. The bird is only being pulled, the weight of the bird only goes straight down, right? So for it to remain in equilibrium, the two horizontal components of the tension force on either side of the bird must cancel out, right? And then the vertical sum of the two tension components on either side have to be equal in magnitude to the weight in order to oppose the weight. Okay, so since the horizontal components cancel out, we have to figure out what the vertical components, which can be done with we can figure out the vertical components using trigonometry. So if the tension in the rope is T, then we can make the following equation, right? So W, which is the weight of the bird, is going to be equal to 2t sine theta, where theta is the angle between the horizontal and the rope, the bending rope. So why, you may ask? Well, remember, the vertical components of the rope have to sum up to equal the magnitude of the weight, right? And so there's going to be a tension pulling from each side, and they're going to be the same tension since the bird's at the midpoint, right? And so to figure out the vertical component of the tension on one side, right, we need to take sine theta, t sine theta, right? Because sine theta is opposite over adjacent, and this opposite force over here is what we're looking for. And since the tension is pulling from both sides, right? The tension's on both sides, right? That's why we need to double it. So yeah. All right. So then we can rearrange the equation we obtained previously to W. So we obtained previously W is equal to, oh, that's a mistake. W is equal to 2t sine theta, not t sine theta divided by 2. We can rearrange that to t is equal to W divided by 2 sine theta. And that is our final expression. And this is a really significant result, since it shows that the angle theta can actually determine whether the tension in the rope is greater than, equivalent to, or less than the weight of the bird. For example, if the rope is almost horizontal, right, or in other words, theta is under 30 degrees, right, though we can see that the tension in the rope is actually going to be greater than the weight of the bird, right? But then if theta is a lot larger, like say 60 degrees, right? Remember, sine 60 is root 3 over 2. If you do the math, you'll actually see that the weight of the bird is going to be greater than the tension in the rope. Okay. So next, we're going to talk about normal force, and normal force is a component of force that usually acts opposite to gravity and supports objects. For example, there's a normal force acting on me that as I'm sitting in my chair right now to prevent me from falling through the ground, right? So essentially, it usually just acts orthogonal or perpendicular to surfaces. And then to add to that, we have friction force, and friction force is the force between two surfaces when they slide past each other, are opposite to the direction that each object is sliding. So there are two types of friction. Static friction is the friction between surfaces that rest, and the dynamic friction is the friction between two objects that are actively sliding against each other. And friction is calculated by multiplying the friction coefficient by the normal force acting on the object. So in other words, F is going to be equal to friction coefficient, which we use this symbol, and then we're going to multiply that by F of n, which is the normal force. Okay, so this should be problem number 4. So for an object on a this is still normal force. For an object on a ramp shown below where gravity is acting on the object, the normal force can be calculated as W, which is the weight of the object, times cosine theta, which is the angle of the incline angle of the ramp. And the force parallel to the ramp is going to be W sine theta. And you can see why, right? And it can be proven that the angle formed by the ramp is the same as the label angle on this other triangle that we made here. And we're not going to go over that proof, but this is still a very significant result. Okay, now we have problem number 4. So you're trying to push a box of weight 10 kilograms up a ramp with an incline angle of 30 degrees. Assuming the static friction coefficient on the ramp is 0.6, determine the minimum force you must apply to budge the box. Okay, so this one we need to draw a force body diagram, and there are quite a few forces at play here. So naturally, there's going to be gravity, which is W, and then the normal force tries its best to oppose gravity, but it's always orthogonal to the surface, right? And so because it's not going to be enough magnitude-wise, there's going to be another component F that balances the equation there. That's like what we talked about earlier, right? There's a component of the force that goes parallel to the ramp, right? And there's in addition to the normal force. So assuming the static friction is enough to hold the box in place when it is at rest, in other words, the force F is going to be less than friction, all right? The force A, which we need to apply to budge the box, is going to be greater than the sum of those two. Okay, so putting what we just discussed into equations, we obtain the applied force is going to be greater than the friction, the force due to friction, and then the other force that is as a result of gravity. So we need to do some rearranging to figure out exactly what we need to calculate, right? So A greater than F of F plus F, and then we rearrange that to, or not rearrange, we actually substitute. We substitute in A is going to be greater than the friction coefficient times the normal force, because remember, that's what defines friction, plus F, which is the force due to gravity. And then if we do some even more substitution, right? A is going to be greater than friction coefficient times the weight of the object times cosine theta, and then plus the weight of the object times sine theta, right? When we talked about that earlier. And then finally, we're going to get A is going to be greater than friction coefficient times the mass of the object times gravity times cosine theta, plus the mass of the object times gravity times sine theta. Okay, so we know our friction coefficient is 0.6, our mass is 10 kilograms, and the angle is 30 degrees, right? So then if we substitute in those values, the applied force is going to be greater than 0.4 times 10 times 9.81 times cosine 30 plus 10 times 9.81 times sine 30. And then if you plug all that into your calculator, you're going to end up getting that it's going to be equal to 100, right? 100. So that means the applied force that you have to apply is going to be greater than 100 newtons. If you apply more than 100 newtons of force, you're going to start moving the box on the ramp. Okay, so let's do a little review. Today we learned about Newton's first and second laws. We learned what force is as well, and then we learned about a lot of different types of forces. The ones we did a little more exploration on are tension, normal, and friction force, and we'll get to the other ones later, don't worry about that. And we discovered a lot of nuances about the behaviors of tension, normal, and friction force, and we did this by solving various problems. So yeah, thanks for watching, and please check out our IB Comp Sci and IB Bio videos as well. In the next video, we're going to continue with force, and I believe we're going to start with Newton's third law and move from there. Thank you for watching. Bye.